Present the conference. Super large-scale optimization algorithms. The material of conference was organized by the engineer Jesus Velasquez Bermudez, Ph.D. From the simplex method to multi-problem models, large-scale optimization meets artificial brains, moving toward mathematics-based general artificial intelligence. Lecture edited by Jesus Velasquez Bermudez, who, in 2024, won the Artificial Intelligence Award of the Industrial Engineering and Operations Management Society, IEOM. PDC Ingeniería. Learning to make algorithms. At 25 years old, Velasquez Bermudez founded PDC Engineering, starting his career as an investor in the operations research business. PDC invested $400,000 current dollars in a ModComp Classic 7870 minicomputer, to solve complex math problems. PDC may be the first type of Silicon Valley company in Latam. The main optimization algorithm made at PDC was PDC Primal Dual. A bounded primal dual simplex algorithm, with multi-pricing, base inverse in product form, and handling the functional matrix and compact constraint blocks. Pivot and complement heuristic to accelerate MIP problems. Bender's partitioning and decomposition algorithm, using a variation of the standard primal dual method, to handle Bender's cuts as a dense matrix, and compact matrix generation. By then, PDC Primal Dual might have been competitive at the level of today's Cplex, or Gurobi. In 1962, the Dutch mathematician Jacques Benders publishes his theory of partition that is a transcendental step, not the first, in parallel computing, aimed at solving complex mathematical problems, dividing them into more elementary subproblems. The first large-scale algorithm assembled by the scientific director of HI was the Benders partition algorithm. This algorithm was implemented more to decrease the memory used by the models, since only 1 MB of RAM was available in the ModComp 7870. Benders' theory became the backbone of the large-scale algorithms developed by Velasquez Bermudez. The article, The Benders Decomposition Algorithm, a Review, presents the state-of-the-art of Benders in 2026. The green bar graph presents the history of Benders through 2016, measured based on published articles. The Benders algorithm is the most widely used by HI to solve large-scale problems. The black line presents the growth of Benders in HI, indicating the variations in the theory of Benders made by HI. After 2016, growth has continued in the development of Benders to build artificial brains. In 1980, PDC was one of the few companies using Benders. HI's knowledge at Benders has been accumulated over 45 years, making HI a leading and expert company in the field. The basic Benders matrix structure is the dual-angular one. The coordinator, linked to the coordination variables, and the subproblem, linked to subordinate variables. The subproblem provides information to the coordinator by the dual variables associated with its constraints. The coordinator takes the information from the primary level and incorporates it in the form of hyperplanes, Benders cuts, limiting the feasibility region for the optimal solution of the coordination variables. The algorithm defined by Benders is convergent and solves the original problem. Through the solution of the coordinator problem, it applies only to linear subproblems. Primal dual surrogate algorithm, theory, and demonstration. In 1970, Harvey Greenberg and William Pierscala wrote the seminal paper, Surrogate Mathematical Programming. PDS, Primal Dual Surrogate Algorithm for Nonlinear Programming, was devised by Jesus Velasquez Bermudez in 1974, at the age of 22, and was implemented in 1980. In 1986, PDS was awarded with the Alberto Leon Betancourt Prize in Operations Research by the Colombian Society of Electrical Calculation and Operational Research, ACIO, award. The Colombian Association of Systems Engineers, ASI, and ACIO were integrated under a single association, ASI. There are two problems to be aware of in the PDS algorithm. The original problem that we will call P, which has a system of vectorial constraints in the form of inequality, gx less than or equal to vector b. The second, the surrogate that we will call S of lambda, which is a derivation of the original. Lambda corresponds to the Lagrange multipliers of the constraints of the original problem, so S is a function of lambda. S has a single constraint that is constructed from a weighted sum of the original constraints times their Lagrange multipliers. The objective function, fx, and the vector function gx are assumed to have continuous partial derivatives. The vectors L and U are limits that are part of the original constraints. The vector of Lagrange multipliers is non-negative. The constraint of S is obtained by replacing the set of M constrictions of P with a linear combination of them. When lambda is equal to the Lagrange multipliers of P, the problem S, with a single constraint, solves the problem P that is M constraints. The idea is to design an algorithm that, when solved, solves P. PDS works in two levels. First, in a dual surrogate level, PDS moves the dual variables lambda to minimize z of lambda. Second, in a primal surrogate level, PDS moves the primal variable x, to solve s of lambda, and evaluate the gradient of z of lambda. Since its inception in 1980, the PDC been used in several algorithms. Its first use was as part of the PDC primal dual algorithm, in 1980. Mainly as cut shots for MIP problems. Since 1990, with the first version of Optex, PDS was incorporated, to compact the database into a multi-level Bender's algorithm, and surrogate programming is currently critical in the management of the hippocampus and hypothalamus of the artificial brains that Hai is investigating. Case, economic load dispatch including transmission losses. The GAMS program uses in the first phase, primal, the CONUP algorithm to solve the nonlinear problems. In the second phase, dual, it uses the maximum descent method based on the subgradient of the surrogate objective function. The following figure presents the results obtained for the case presented by GAMS. It can be seen that in iteration 4 the gap in the target cost has been closed. Those interested in learning more about the theory and demonstrations of the PDS, can review the draft. Chapter 28c, Subrogate Programming and Primal Dual Subrogate Algorithm. In 1981, PDC began the process of developing large-scale algorithms, to accelerate the speed of solving large problems. In 1981, PDC implemented the Bender's decomposition algorithm to solve water resource problems using stochastic optimization. The hierarchical structures produced by large-scale methodologies do not simply correspond to mathematical artifices to solve large-scale problems. These structures are linked to representations of reality. To model a real system, two visions are possible. Top-down implies a monolithic vision, based on sequential synchronous mathematics. From the bottom up, a parallel atomized vision, based on parallel asynchronous mathematics, oriented to large-scale optimization methodologies. The basic Bender's matrix structure is the dual angular one. However, there are many real cases in which the matrix associated with the subordinate variables has a diagonal structure, which allows the variables to be segmented into n independent groups. Then, the subproblem can be decomposed into n independent subproblems, or decomposition dimensions, which can be solved in parallel. Examples of decompositions dimension are periods, business, regions, sector, functions, general entities, and random scenarios. However, there are many real cases in which the matrix associated with the subordinate variables has a diagonal structure, which allows the variables to be segmented into n independent groups. Then, the subproblem can be decomposed into n independent subproblems, or decomposition dimensions, which can be solved in parallel. Examples of decompositions dimension are periods, business, regions, sector, functions, general entities, and random scenarios, which produces n Bender's cuts. Decoupled decomposition Benders, or decoupled Bender's cuts, DBC, corresponds to a variation of BT, that solves in each iteration a small subproblem for each decomposition dimension. DBC solves W small problems and generates one decoupled cut for each W. The cuts are coupled in the objective function. It is easy to prove that decoupled decomposition is faster than standard decomposition. Next, the geometric behavior of the two algorithms is analyzed, in order to intuitively understand the decoupled decomposition process. To do this, we will work on the feasible zone of the dual problem of the subproblems, which limits the dual variables pi w. A problem that has two subsystems w, symmetric dual feasible zones, defined by a closed polygon of 6 points, it is considered. Let us assume that the optimal solution of the integral problem is given for the values pi 6,1 in subsystem 1, and pi 3,2 in subsystem 2. The table presents the hypothetical solution of the problem for the coupled case, that is the standard Bender's method. In each iteration, the integrated subproblem will report solutions for the dual variables of the two subsystems. The end of the standard coupled process will occur when the optimal solutions in the two subsystems coincide with the optimal solution of the integrated model, in this case in iteration 6. If the cuts are decoupled, in iteration 2, the two optimal solutions have already been obtained. For subsystem 1, in iteration 1, and for subsystem 2, in iteration 2. And therefore, the solution of the decoupled method would have already been achieved. Clearly, it is not possible that the coupled algorithm may require fewer iterations than the coupled system. Additionally, it is possible that, during the coupled optimization process, the optimal solution for each subsystem is listed more than once. This is useless information, for which you pay a computing time. To the extent that the system is more complex, the difference between the two algorithms will be greater. The graph presents a benchmark coupled versus decoupled Bender's cuts. In it you can see that the decoupled algorithm is 2.8 times faster to obtain the optimal solution. But if the optimality gap is relaxed to 0.005%, this difference can reach 16 times faster. The results come from an application of unit commitment in the electricity sector. In asynchronous parallel optimization, it can assign as many processors as there are decomposition dimensions, provided availability exists, plus one processor for the coordinator. All processors work all the time, minimizing the idle time of the multi-core computer. PDC solved multiple real problems in water resources engineering and flow prediction algorithms. The most important was the master plan for hydraulic resources of Zone 1 of Zulia. A mixed integer mathematical program, MIP, had more than 30,000 variables, and was solved using Bender's partition theory and the pivot and complement heuristics in the ModComp classic computer. PDC generated invaluable insights in solving complex mathematical models with limited computational resources. This knowledge was capitalized years later in Optex. Decisionware. Making special large-scale algorithms. Bender's decomposition using unified cuts. This methodology can only be applied when the dimensions of decomposition are periods and/or random scenarios. In 1990, Velázquez-Bermúdez, 1995, 2002, raises the theoretical analysis, related with the solution of large optimization problems, using the partitioning Bender's theory applied to the decomposition of dynamic systems, and stochastic optimization problems, when they have a special structure. It lies in the dual feasibility zone of the subproblems, when it is equal for all subproblems. In such a case, solving a single subproblem, it is possible to generate Bender's cuts for all subproblems. The application of UBC speeds up the solution time, and make possible the solution of a large-scale optimization problem, as a coordinated sum of very simple problems. In the white paper Bender's decomposition unified cuts, the UBC is reviewed, complementing it with the implementation, analysis, and the presentation of experimental results, using models oriented to the electricity sector. Resuming. SBC, standard Bender's cuts. It corresponds to the methodology proposed by J.F. Benders that resolves a single subproblem, that integrates the subproblems for all decomposition's dimensions, and generated only one cut in each iteration. DBC, decoupled Bender's cuts. It corresponds to a variation of BT that solves in each iteration a small subproblem for each decomposition dimension. DBC solves W problems, and generates one decoupled cut for each period. The cuts are coupled in the objective function of the coordinator model. UBC, unified Bender's cuts. When the mathematical conditions are met, It corresponds to a variation of BT that solves in each iteration a subset of all subproblems. Solving only one subproblem, UBC generates decoupled cuts for each decomposition dimension, periods and/or random scenarios. The cuts are coupled in the coordinator. UBC is applied to both stochastic and/or time decomposition dimensions. The great advantage lies in the fact that, by solving a single subproblem, cuts are generated for all subproblems, which will significantly increase the speed of solution of the integrated problem. The problem, or problems, that need to be solved is a problem of mathematical logic and artificial intelligence. Examples of the solution of an electrical system dispatch model are presented, with a linear model and 24 periods. 3 sequencing methods are used in a maximum of 24 iterations. The following solution times are compared: 3 sequencing methods, DCB decomposition, using the GDDP model methodology. GDDP with unified cuts is faster than GDDP with decoupled cuts, up to 1.68 times. This ratio increases as the amount of points growth. Deterministic results. MIP unit commitment. In all cases was established that maximum process time was 1000 seconds, in 2 cases the full problem don't get a solution under the maximum time. Multi-level Bender's partition algorithm. In 1990, Decisionware implemented the first version of Optex to solve the problem of the expansion of the largest brewing company in Colombia. The multi-level Bender's theory presents the generalization of the Bender's theory, BT, for several typical cases, where the multi-level structure of the optimization problem enables the effective utilization of BT. The analyzed cases are: decomposition theory is useful when it is possible to grouping variables subordinated into independent sets to formulate multiple subordinate subproblems. In this case, the variables of coordination are also called coupling variables. Multi-level theory is used when there is a multi-level hierarchical relationship within the variables of the problem, and it is possible, inside to subordinate variables, to select a new set of coordination variables for establish an additional level of partition. Multi-level decomposition theory is the result of the combination of the 2 previous theories. Then, the modeling of large-scale systems can be defined as the process of dividing a large problem in 2 or more subproblems, with the aim of reducing the dimension of the problem, since the computational complexity grows exponentially with the dimensionality. In this way, the sum of the complexities of the subproblems plus the overhead must be less than the complexity of the integrated problem. In the original way to implement multi-level theory, each hierarchical level returns to the top level only when it has obtained the optimal solution to the problem, that is parameterized by the decision vector y, preset at higher levels. This implies that at lower levels nested cycles is performed for the upper levels. But more efficient methods using cross-decomposition concepts and parallel asynchronous optimization should be implemented. As reference, a typical list of cases in which it is possible to apply partition and/or decomposition schemes. Investment planning. Usually problems oriented to determine investment plans have a structure in which the investment's variables control the operations variables. Many of investment's variables are binary, and the partition allows to handle 2 problems with different mathematical characteristics. The coordinator model, a mixed integer programming, MIP or MIMP, and the operations subproblem, a linear programming, or nonlinear programming, based on continuous variables. Multi-sectoral planning, optimizations models that link various sectors. It is possible to select as coordination variables transfers of goods, services, and resources between sectors, defining the production variables at the level of decomposition subproblems associated to each of the sectors. Multi-area, or multi-region planning. When performing optimizations that integrate several areas, it is possible to select transfers of goods, services, and resources between areas as coordination variables, and define at the level of decomposition subproblems associated to operations in each of the area. As an example, an electrical system that interconnects several regions of generation and/or consumption. From the hierarchical standpoint, a sector may be composed of multiple areas. The concept of area may be a logical or physical, since also the area may be associated to regions, teams, market agents, etc. Multi-period planning, mathematical models that integrate multiple periods. It is possible to select transfers of goods, services, and resources between periods, variations of inventories or stocks, as coordination variables, and define at the level of subproblems the production in each period. Discrete time models always have this possibility. Stochastic optimization, an approach oriented to develop optimization processes that consider the possible scenarios of random variables that affect a system. It is normal to define a set of variables associated with the decisions to be taken regardless of the realizations of the stochastic process. This feature depends on variables associated to the simulated operation, conditioned on a possible scenario. Under this scheme, it is possible to define the coordination variables as those that are independent of the scenarios, and to define in the decomposition level, subproblems associated with each scenario. In this case, normally, all subproblems have the same matrix structure, allowing to design efficient algorithms for the joint solution of all the subproblems. Database compaction using surrogate programming. Since 1990, with the first version of Optex, surrogate was incorporated to compact the database into a multi-level Bender's algorithm. This allows for no explosions of Bender's cuts as the optimization process progresses. On the other hand, surrogate programming is currently critical in the management of the hippocampus and hypothalamus of the artificial brains that Hai is investigating. Bender's partition and decomposition framework. In 1990, simultaneously with the development of the multi-level Bender's algorithm, DW integrated the two multi-level theories, partitioning and decomposition. The first implementation of the Bender's partition and decomposition algorithm was in 1990, during the implementation of the Bavaria Industrial System Corporate Planning, PCSI, a DSS of strategic and planning models. The tri-level Bender's algorithm was used to resolve the issues using Intel 386-486 CPUs. By 1998, PCSI enabled the planning of a beer supply chain of 18 production plants, 42 bottling lines, and more than 230 SKUs. The models have been used for over 25 years. The previous cases may occur in a hierarchical multi-level structure, allowing that in a model may be performed more than one partition and/or decomposition. The definition of sectors, areas, functions, etc., depends on the most convenient point of view to mathematical modeler. The most important thing about this process is that the two extreme levels, the upper coordinator, and the bottom subproblems, or atoms, are the same regardless of the criteria with which the intermediate levels are assigned. The most important aspect about this process is that the two extreme levels, the upper coordinator, and the bottom subproblems, or atoms, are the same regardless of the criteria with which the intermediate levels are assigned. If you analyze the hierarchical structure that is formed, for a large problem, under the partition and decomposition schemes, you find total similarity with the structure of the human cortex. If you analyze the hierarchical structure that is formed, for a large mathematical problem, under the partition and decomposition schemes, you find total similarity with the structure of the human cortex. The image presents three visions of this similarity. Human neocortical structure, Jeff Hawkins' artificial intelligence structure, and large-scale mathematical programming structure. Everything indicates that the structure and joint functioning of the neocortex and hypothalamus is like the structure of the most advanced optimization algorithms. This strong relationship can serve to deepen the knowledge of the two disciplines, artificial intelligence and mathematical programming. The diagram presents the hierarchical structure of decomposition and partition of an oil and gas company. Based on the concepts of partitioning and decomposition, it is possible to decouple a system, to obtain vertical structures partially similar like of the human neocortex. The evolution of mathematics has allowed us to better understand systems, evolving from monolithic to large-scale modeling. To visualize the difference between the information provided by the solution of a monolithic model, and the coordinated solution of multiple atomized models, we can think in a medical examination based on a photograph, and another based on an X-ray. The photograph does not allow us to understand what is happening inside the human body, X-rays do. Internal visualization of a system is an advantage that cannot be achieved with a monolithic view, which only provides aggregate information, Atomization allows us to understand how the system is assembled and how information flows within it. Dual dynamic programming, DDP, or nested benders, NBD. Richard Ernest Bellman was born in 1920 in New York City to non-practicing Jewish parents of Polish and Russian descent. Beginning 1949, Bellman worked for many years at Rand Corporation, and it was during this time that he developed the dynamic programming. The structure of dynamic programming involves the joining in time of a chain of all similar states. Each state is composed of two types of variables. State variables which represent the evolution of the system, for example, stocks, storages, capacities, and on/off state. And control variables that represent the activity levels in the production system. The solution of a problem via PD is carried out in two phases. Phase 1, backward, from back to front, generate the optimal possible trajectories. And Phase 2, forward, from front to back, from the initial conditions, the optimal trajectory is built. The original approach to discrete dynamic programming is based on a table-based numerical optimization process, T state variables combined with T1 state variables. For models with many state variables, this generates a large computational drawback called cursive dimensionality problem. That implies that real problems with multiple state variables cannot be solved exactly by DP, because it is necessary to solve ST by ST1, reduced problems for each period T, where ST represents the number of state variables in T. As a solution, a group of algorithms was generated that were called nested benders. In 1994, Mario Pereira published the article, Stochastic Optimization of a Multi-Reservoir System, Decomposition Approach. That was the first presentation of the DDP. In 1999, Velázquez Bermúdez, Restrepo, and Campo published a review of DDP, Dual Dynamic Programming, a note on implementation. Dynamic programming is characterized by having control variables and state variables, whereas dual dynamic programming only has state variables. An alternative is to define the first period, between period 1 and period T1, as a coordination problem and the last period as a slave period. In another case, the first period is classified as a coordination problem and the rest are slave subproblems. Dual dynamic programming, DDP, or nested benders, NBD. Several researchers used the ideas of discrete dynamic programming to generate a continuous version of PD. That was called stochastic nested benders. The book Introduction to Stochastic Programming presents a summary of cases. DDP can be defined as composed of three types of problems. Pure coordinator, related to the first period. Pure subproblem, related to the last period, and coordinator, subproblem, related to all intermediate states. This structure allows for multiple alternatives in the algorithm flow, which means that multiple versions of the algorithms exist. Three main heuristics are used in deciding which way to move the forward-backward process, Thompson, 1997, Murphy 2013. Such heuristics are fast forward, which aims to descend the tree whenever possible. Fast back, which aims to go back up the tree as far and as fast as it can wherever possible. Fast forward, fast back, which, as the name suggests, is a combination of the two methods above. In this case, we have a switch that puts the algorithm in either descending or ascending mode. GDDP. Generalized Dual Dynamic Programming. Version 1. GDDP, Generalized Dual Dynamic Programming. And another of the algorithms developed was the NLDDP, Dual Nonlinear Dynamic Programming. This was in 2004 and presents the integration of the algorithm Geoffrion's generalized Bender's algorithm with dynamic programming. PD and GSDDP have the same structure, including state variables and control variables in a differentiated way. The application of benders involves the use of the principles of partition and decomposition. First, the problem is divided into control variables and state variables, generating a subproblem dependent on the state variables. The problem is then divided into the t-period state variables and the t+1 period state variables. The decomposed problem has the following characteristics. The coordination problem, only in the state variables, can be solved using the DDP. The slave problem of control variables can be solved using decomposition Bender's theory, with unified cuts. The coordinator problem is formed by problems of state variables, which control future cost, and a subproblem of production. Communication between everyone follows the rules of unified Bender's cuts. The general coordinator can be solved based on the DDP principles. The subproblem for all states may be solved based on UBC. Two types of cutting are generated. Weight xt1, xt, equals Cobb-Douglas supply function. Alpha t plus 1 xt equals future cost function. GDPP is 7.69 times faster than DDP. High develops large-scale optimization algorithms to accelerate the solution of high-complexity mathematical problems. In 2008, EW made changes to the version of the GSDDP it used. The change consisted of replacing the DDP-type coordinator with an integrated coordinator of the standard Bender's type. The production subproblem remained using unified Bender's cuts. GSDDP includes risk management, from a scientific approach, using the conditional value at risk. The article GSDDP Generalized Dual Dynamic Stochastic Programming Theory and Electric Sector Applications presents the results of the research carried out in 2018. For the analysis of different experiments, a case published by the IEEE was taken as a reference, which was modified to analyze several cases. The figure presents the base case, which is the size of the Panamanian electricity system, in 2012. The figure presents system demand. Below is the formulation of the dispatch model, which is assumed to be mixed linear model. Indexes, sets, and parameters are presented. The image presents the variables and equations of the model. The formulation of the model, in GSDDP format, is presented below. The variables are divided into state and control. Dispatch is mixed linear, because the state of the thermal power plant, on or off, are state variables. GSDDP Generalized Stochastic Dual Dynamic Programming version 2. To speed up the solution time of large-scale problems, High created the algorithm GDDP, Generalized Dual Dynamic Programming. GDDP is oriented to solve dynamic optimization problems, integrating the Bender's theory and dynamic programming approaches. Based on the dynamic programming approach, GDDP makes a distinction between state variables and control variables. This distinction permits a more detailed algorithm in which the subproblems are smaller than in the algorithm's nested Bender's decomposition, NBD, widely used in the economic dispatch of power systems. The main limitation of NB, including dual dynamic programming, DDP, is that they only solve linear models, then GDDP is more robust than NBD. As you see in the table. The table presents a benchmark, realized by High, between standard GSDDP and standard SNBD, stochastic nested Bender's decomposition, like SDDP, using a stochastic linear economic electricity dispatch. The experiments show that the low complexity of the case does not always justify the large-scale methodologies. The best GSDDP option is, approximately, 100 times faster than SNBD, and the best GSDDP with NBD coordinator is, approximately, 15 times faster than SNBD. The following table and image resume the study of behavior of GSDDP for a stochastic mixed linear economic electricity dispatch. The decrease in the solution time per scenario, when increase the number of scenarios, is a measure of the learning capacity of the GSDDP. The idea of sliding optimization is that although an integrated system implies that all variables are related and that therefore their optimization must be united, to the extent that two variables are distant in spacetime this relationship tends to fade, and it can be thought that at the two extremes the influence of the associated variables tends to cancel out. Sliding optimization consists of dividing spacetime into sub-problems that are solved independently and then added in such a way that in the end a problem that covers spacetime completely is solved. In the aggregation phase, the starting points correspond to the solutions obtained in the previous step. This diagram shows a multi-level structure that can be solved using the combination of MBP and GDDP, producing atoms, mathematical neurons associated with pairs of time and random scenarios. The image can be associated with the vertical connectivity of an artificial brain to face the design problem of a global multi-business organization. Traffic network optimization modeling. The figure shows the conceptual representation of the proposed methodology. The distributed optimization decomposes the network-level problem into several standalone intersection-level subproblems and solves them in parallel. The decomposition is achieved by identifying the constraints that represent interrelationships between subproblems and relaxing them. Distributed coordination pushes solutions towards global optimality by exchanging information among subproblems that share a relaxed constraint and reinforcing the relaxed constraints in subproblems by incorporating the information that is received from other subproblems in them. The figure shows the conceptual representation of the proposed methodology. The distributed optimization decomposes the network-level problem into several standalone intersection-level subproblems and solves them in parallel. The decomposition is achieved by identifying the constraints that represent interrelationships between subproblems and relaxing them. Distributed coordination pushes solutions towards global optimality by exchanging information among subproblems that share a relaxed constraint and reinforcing the relaxed constraints in subproblems by incorporating the information that is received from other subproblems in them. The figure shows the conceptual representation of the proposed methodology. The distributed optimization decomposes the network-level problem into several standalone intersection-level subproblems and solves them in parallel. The decomposition is achieved by identifying the constraints that represent interrelationships between subproblems and relaxing them. Distributed coordination pushes solutions towards global optimality by exchanging information among subproblems that share a relaxed constraint and reinforcing the relaxed constraints in subproblems by incorporating the information that is received from other subproblems in them. The figure shows the conceptual representation of the proposed methodology. The distributed optimization decomposes the network-level problem into several standalone intersection-level subproblems and solves them in parallel. The decomposition is achieved by identifying the constraints that represent interrelationships between subproblems and relaxing them. Distributed coordination pushes solutions towards global optimality by exchanging information among subproblems that share a relaxed constraint and reinforcing the relaxed constraints in subproblems by incorporating the information that is received from other subproblems in them. Finally, the diagram presents the proposed two-level structure using Bender's decomposition. Perhaps the solution time may be speed up if more levels are introduced in the hierarchical structure. In this case, it is proposed to include a level associated with the main traffic corridors that interconnect the region. It is possible to extend the proposed model using the concepts of autonomous real-time optimization. The approach may be conceived as an artificial brain composed of a network of mathematical models, general coordinator, the master problem traffic corridor coordinators intersection subproblems. The communication between the algorithms of mathematical problems must be asynchronous, operating continuously. Hypothalamus artificial intelligence. Creating artificial brains. In 2022, HI developed the multi-Bender's decomposition algorithm, following the thousand-brain intelligence theory formulated by Jeff Hawkins. Jeff Hawkins is an advanced researcher in the application of neuroscience to the development of artificial intelligence. As a result of his studies at Numenta Incorporated, Hawkins proposes the sparse artificial intelligence model. Jeff Hawkins' theory is summarized in the article. Why does the neocortex have layers and columns? A theory of learning the 3D structure of the world. Hierarchies can be associated with multiple views of the same system, as Jeff Hawkins proposes. All models of the same system must work cooperatively. In an artificial hypothalamus, the situation can be similar, as there are multiple views of the same system. Considering the vision of large-scale optimization as multiple points of view, Hai developed the Bender's multi-decomposition methodology. Let's consider an oil and gas system, a company, which can be seen, broken down from 3 points of view: business management managing regions, and organizational management. If you want to break down the problem, using Bender's decomposition, you can select the vice presidency of the regions as the first level. Another alternative is to select the vice presidency of business as the first level, and finally, the first level can be chosen as the vice presidency of organizational management. Since all visions correspond to the same system, all problems, regardless of point of view, must produce the same result. Mathematically, the numerical result must be the same, the solution time must be different, depending on the input parameters. If an administrative criterion is used, all problems are equivalent. Using Bender's decomposition, we would have 3 coordination problems that are equivalent. If the 3 problems are solved independently, in parallel, any one of them will give the optimal solution at some point. If all problems are solved to the end, the set of cut planes would be equivalent in all 3 cases and could be included as part of any problem. It is also possible to form a coordination problem, with cutting planes coming from the 3 subproblems. The sets I to B, I to R and I to F differentiate the number of cuts generated by each subproblem for each dimension of decomposition. These sets will be independent of the index associated with the decomposition dimension and will be common to all decomposition subproblems. These problems can be solved asynchronously in parallel. The cutting planes can be shared between problems, since they correspond to a way of seeing the restrictions that have been eliminated from the coordinating problem. There are multiple alternatives for the architecture of the decomposition. One of them is to have a general coordinator, the board of directors, and at the second level we have a subproblem for each entity in the decomposition dimension. The number of subproblems at the second level is fixed and independent of the decomposition architecture. Running the MBD requires a dedicated processor for the coordinator, a dedicated processor for round-robin management, and a cluster of processors dedicated to second-level problems. At the second level we have a subproblem for each entity in the decomposition dimension. The number of subproblems at the second level is fixed and independent of the decomposition architecture. The solution can be visualized as a traditional decomposition algorithm, where information flows vertically, as in the human cortex. The multi-Bender's decomposition algorithm, MBD, can be seen in another way, as a network of mathematical artificial neural networks, which all communicate with each other, as is supposed to occur in the human hypothalamus. In simple multi-level Bender theory, in many cases there is no obvious hierarchical order for partitioning. MBD is a new approach that takes advantage of formulating multiple equivalent problems, one for each point of view, and formulating an extended coordinator model that integrates all points of view. Building artificial brains. The artificial brains have been designed, following the conceptual results presented in reports conducted by neuroscience experts. In the process, the similarity between a human brain and an artificial brain for an organization has been discovered in every aspect. If you look at the problem of building a brain, the first big problem to face is the architecture of the cortex. Hundreds of millions of connections of human neurons. In the artificial cortex, there will be hundreds of millions of connections of mathematical superneurons, in which each neuron must be built according to the type of function it must fulfill. The work to be done is monumental, and it is utopian to think that a superior being, when building a human brain, would do it manually. The first thing he should have developed is the algorithm that produces human beings automatically. In the same way, you can't aspire to build an artificial brain if you don't have the artificial intelligence that produces artificial brains. In 2022, to handle the concept of mathematical intelligence, Hai developed the concepts of mathematical artificial neural nets, MANN, which complement the concepts of artificial neural networks, ANN. In 1943, Warren McCulloch and Walter Pitts created the concept of artificial neural networks. They published the paper, A Logical Calculus of the Ideas Immanent in Nervous Activity. McCulloch and Pitts tried to understand how the brain could produce highly complex patterns, by using many basic cells that are connected. They designed their system based on as they believed our brains work, and patterned it after the biological model of how neurons work with each other. The neural networks were growing, and in practice they took the name of artificial intelligence, displacing other methodologies and technologies that also generate artificial intelligence in the machines. An artificial neuron is a mathematical function conceived as a model of biological neurons. Artificial neurons are elementary units in an artificial neural network. The artificial neuron receives one or more inputs, representing excitatory postsynaptic potentials and inhibitory postsynaptic potentials at neural dendrites, and sums them to produce an output, or activation, representing a neuron's action potential which is transmitted along its axon. Usually each input is separately weighted, and the sum is passed through a nonlinear function known as an activation function, or transfer function. The transfer functions usually have a sigmoid shape, but they may also take the form of other nonlinear functions, piecewise linear functions, or step functions. They are also often monotonically increasing, continuous, differentiable, and bounded. Starting from the perceptron, the first artificial neuron created, the knowledge of neuronal modeling has evolved, currently having multiple types of artificial neural nets. This new type of neuron will be called mathematical artificial neuron. Its name was derived from the fact that the neuron is built, based on mathematical models that represent a system, and that it does contains logical or intuitive elements. The mathematical artificial neuron is a mathematical model, presumably of optimization, which results from the partitioning and decomposition of a monolithic problem, into an atomized model, following the mathematical laws of large-scale mathematical modeling. Two mathematical artificial neurons communicate with each other, forming a network of mathematical artificial neurons. Communication occurs in two directions between the two neurons. The communication protocol between the two neurons is defined by mathematical laws developed to solve atomized problems. The modeler can choose the protocol, but not the communication process, which for optimization is based on the scientific laws of duality theory, and for equilibrium problems in mathematical programming with equilibrium constraints, PEC. A mathematical neuron represents a robot, which can communicate with another robot, autonomously, since it knows the mathematical rules that it must respect. This is what happens in the human brain, where autonomic systems communicate with each other to make decisions. The mathematical artificial neuron is the technological evolution from the biological neuron, typical of mental intelligence, to the neurons necessary to represent mathematical intelligence, which until now are not produced by the human being. Like all mathematics, theory is cadent, and for those of us who already work in high-complexity mathematical modeling, it is the logical step we must take. It's just widening the look, and thinking a little outside the box. The mathematical artificial neuron is a mathematical superstructure, representing a complete system. A mathematical artificial neuron network can be a neuron of a larger mathematical artificial neuron network. This law of transitivity is typical of large-scale modeling. This process can be repeated, until the smallest mathematical artificial neurons, the atoms of the system, are obtained. A large-scale system can be represented by a mathematical artificial neuron, and covers multiple subsystems, where each of them can be represented by a mathematical artificial neuron. Using large-scale methodologies, the mathematical artificial neuron can be divided into two, or more, mathematical artificial neurons, forming a mathematical network of artificial neurons. An artificial hypothalamus is a network of mathematical artificial neurons. Each of them represents a system or subsystem. The difference with large-scale methodologies is that the solution is visualized as specialized communications between mathematical problems, while in the artificial hypothalamus the process is cooperative based on autonomy, distributed, and real-time processing. In addition, there is a standardized language for communications between mathematical artificial neurons. Any type of organization can be represented following these principles. The case of a poultry production system is presented. The system has been divided into 6 subsystems, which together make up the poultry production system. The great contribution of mathematical artificial neuron networks is that they open the way to integrate machine learning operations with the management of mathematical programming models, using 2 standardized paradigms. For example, following the principles developed by Benders, it is possible to build an artificial hippocampus that remain active and useful beyond the duration of a run of a computer model. To do this, the cuts generated in each run must be stored in such a way as that they may be used later. This implies a coordination work, since it cannot be guaranteed that the information as it is produced can be reprocessed later. While all the mathematical support is solid, there is no theory that can indicate which cutting planes should be selected when restarting the model. Problem that becomes big when the size of the database grows. For this reason, it is considered necessary to develop tools, based on traditional artificial intelligence, artificial neural nets, to help the management of the hippocampus database. The idea is that for very large problems, the selection process will include an ANN. This is one of Hai's research projects. Velasquez, in 2021, published on SSRN, the paper Artificial Hypothalamus, Artificial Intelligence and Mathematical Programming Integration, in which the foundations of artificial brains, and more specifically of the hypothalamus, are laid. The article, and others later, carefully studies the relationships between the structures of the neocortex, with those formed when a mathematical problem is atomized, to use large-scale optimization methodologies, oriented to the partitioning and decomposition of systems, and they define the artificial brain in semi-detail. This is a disruptive vision of artificial intelligence, considering the power of computers, the evolution of mathematics, and the Internet of Things. This conference explains in a summarized way this evolution, based on the current state of AI. A complementary document is Artificial Brains, Augmented Artificial Intelligence, Artificial Neocortex plus Artificial Hypothalamus plus Artificial Hippocampus. Enrique Krauss in the prologue of Cyber Leviathan, wrote, Artificial intelligence is restructuring human life in unimaginable ways. With it, certain occupations in which we consider human intellectual and emotional capacity indispensable will end up becoming extinct, replaced by incredibly complex systems capable of emulating it. This makes our situation very different from that of 2 centuries ago. This time the machine will be able to completely replace the human being with his physical and cognitive abilities, and with this he could inevitably deprive a very high percentage of the population of work experience, which has been an essential element in human identity. Thank you for your attention.